Light is everywhere, from the glow of a lamp in your room to the stars scattered across the night sky. But what exactly is light made of? This seemingly simple question puzzled even the greatest minds for centuries. Some people thought that light was made of tiny particles, while others thought it was a wave, kind of like ripples in a pond. These are two very competing ideas. I mean, particles, for example, come in discrete lumps. They are localized, meaning they have a specific location, and each one moves in a particular direction. But waves, on the other hand, are continuous and spread out in space, and they move outwards in many directions at once. So, which one is light? For about a century, scientists leaned towards the particle model, largely because of Sir Isaac Newton and his enormous influence. But in 1801, a scientist named Thomas Young performed an experiment that changed everything. He placed a board with two tiny holes in front of a candle flame and looked at the light on a screen behind it. Because of the two slits, we call this the double slit experiment. Now, intuitively, we might expect to see two bright patches, right? But instead, he saw a pattern that looked like this. Wait, what's going on over here? If light were made of particles, then they would indeed form two patches, just as our intuition suggests. But what if light were a wave, like ripples in a pond? Then a single wave passing through two holes would create two new waves. And these two waves would then overlap and mix with each other. What would happen when these waves mix? Let's think about water ripples. Water waves have peaks and valleys, right? Now, when the peaks of two waves line up, or the valleys line up, they combine to make bigger peaks or deeper valleys. This is called constructive interference. But when the peak of one wave lines up with the valley of another, they cancel each other out, producing almost nothing. This is called the destructive interference, which means waves also show interference pattern. And that's exactly what we see over here. These bright regions are places where the waves add up. The peaks line up with the peaks, or the valleys line up with the valleys. And these dark regions are where the waves cancel out. This is where the peak of one wave lines up with the valley of the other. So look, this means that light must be behaving like a wave. This was the first clear, conclusive evidence in the favor of the wave model of light. And so over the next century, many experiments strengthened this wave picture of light. But then came an experiment that broke everything. Scientists discovered that shining light on certain metals could eject electrons from the surface. We called it the photoelectric effect. But the problem was, not all colors of light could do this. For example, shining red light on zinc would not eject electrons at all, even if that light was incredibly bright. In contrast, even very dim ultraviolet light could easily eject electrons. Now, of course, you can't really see ultraviolet light, but the main question was why? Why did the photoelectric effect depend on color? That is something that the wave model just couldn't explain. And that's when a scientist named Albert Einstein came along. He proposed a radical idea. What if electrons don't absorb light's energy continuously like this, as if light were acting like a wave? What if they absorb it in discrete chunks, like a particle? These packets of light energy are what we call photons. And what if the energy of this chunk, the photon, depends on the color or the frequency of the light? Then the bright red light would consist of many, many photons because it's bright, but each photon would carry very little energy. That's like trying to knock over a bowling ball using ping pong balls. It doesn't matter how many you throw at it, each one carries too little energy to make a difference. On the other hand, even a very dim ultraviolet light would consist of fewer chunks because it's very dim, but each chunk would carry a large amount of energy. That's like using a cannonball. One hit is enough to knock the bowling ball off. This idea perfectly explained the dependence of color or the frequency on the photoelectric effect. Remember that shorter the wavelength, higher is the frequency, and our eyes perceive visible light frequency as colors. So it doesn't matter how many photons you have. It doesn't matter how bright the light is. What matters is how much energy each photon carries, and that depends on the color. And that's why only those colors or frequencies of light whose photons have enough energy to eject the electrons can cause photoelectric effect. And Einstein later won a Nobel Prize for this work. So now we're struck with a very strange situation. We know light behaves like a wave as shown by the experiment of the two holes, which is also called the double slit experiment. But it also behaves like a particle as shown by the photoelectric effect. So what is light? Is it a wave or a particle? Turns out it's neither purely a wave nor purely a particle. Instead, it has properties of both. This is what we call the dual nature of light. It has both wave and particle properties. Today, we think of light as spreading through space like a wave, but interacting with matter, for example, when it is absorbed, in discrete particle-like chunks. Now, if you think light is strange, then you're in for a wild ride. Back in the day, scientists thought the electrons in an atom are revolving around a central nucleus, kind of like planets going around the sun. But a man named Niels Bohr proposed that these electrons can only exist in specific orbits, only at specific distances from the nucleus, like over here or over here. But the electrons can never exist anywhere in between. And so, when an electron transitions from a higher energy orbit to a lower energy one, it has to do so directly, meaning it has to disappear from here and just reappear over here without ever being anywhere in between. And when it does that, the difference in the energy is released as a chunk or a photon of light of very specific frequency. This idea explained why, when hydrogen is heated, its spectrum consists of very specific colors. It is due to these electron transitions between these specific orbits. But the big problem was, Bohr could not explain why. Why is it that the electrons can only exist at specific distances from the nucleus and never in between? And how exactly can an electron transition from a higher orbit to a lower one without ever being in between? This is where a scientist named Louis de Broglie proposed a radical idea. He pointed out something curious. Light, which we once thought was purely a wave, turned out to also show particle behavior, right? So de Broglie asked a bold question. What if electrons, which we usually think of as a pure particle, also has a wave nature associated with it? At first, this sounds very strange. How could that possibly explain anything? But it could explain Bohr's orbits. To see how, think about a guitar string. When you pluck a guitar string, it doesn't vibrate in any way. It can vibrate in specific patterns with one large loop, or two loops, or three loops, right? But it cannot vibrate with a half a loop or 2.5 loops, for example. Those patterns simply don't fit. This means vibrations of only specific energies are allowed. Ooh, so imagine this. What if electrons are not tiny particles going around the nucleus like planets? Instead, what if they behave more like waves vibrating around the nucleus? Then, just like a guitar string, it would only vibrate with, say, 3 loops, or 4 loops, or 5, but nothing in between. That would explain why electrons can only be found at certain distances from the nucleus with specific energies. And so, When the electron in a higher energy state transitions, it has no choice but to directly transition to one of the lower waveforms without ever being in between. And that's how the difference in energy is emitted as a photon of light. Suddenly, Bohr's energy levels made sense. Now, of course, we eventually extended this idea of standing waves to 3 dimensions, but we don't really need to go there. Instead, the big question we can now ask is, does this mean electrons too have wave-particle duality, just like light? Well, the following decades were filled with confusion, debate, and frustrations, but gradually experiment after experiment began to point in the same direction. Yes, electrons also have dual nature. Eventually, scientists repeated the double slit experiment once again, but this time they used electrons instead of light. They fired the electrons one at a time towards the two tiny holes. Each electron hit the screen at a specific spot, just like a particle would. And initially, the pattern was very random. But as more and more electrons were sent through, something remarkable happened. A pattern slowly began to form. Look, this was the interference pattern we saw with the waves. I mean, look, intuitively, I would expect hardly any electrons to land at the center of the screen because there's no hole over here. It's blocked, right? But instead, we get the most electrons landing over here. So how does it make any sense? Well, the writing is on the wall. Electrons also behave like tiny particles when they interact with the screen, but as they travel, they behave like waves, interfering with each other, producing constructive and destructive interference. Electrons, just like the light, show wave-particle duality. And what's even more wild is that this isn't limited to electrons. In principle, atoms, molecules, tennis balls, even you and I all have wave nature. It's just that for large objects, the wave effects are incredibly tiny, so that they are completely unnoticeable, but they're there. And so, zooming out, a seemingly simple question of what is light ended up changing how we think about everything. What began as a debate between particles and waves led us to the idea that all matter and light show this dual nature. This is the foundation of what we call the quantum mechanical model. It's the most successful model we have of the universe at the smallest scale. But it isn't perfect. It doesn't work in some extreme regions of space. And that's good news, because that means there is more to cover. The story of light and matter isn't finished yet.